I have back with us, as hopefully we will kind of make a regular thing, Scott Walter on Wednesday mornings. Scott, how are you doing?
Oh, I'm doing fine. I'm
We
fine.
were just talking about the launch of that vehicle that you've got there in your
Yeah,
assortment of toys.
yeah. Got the real one. Replaces this one that was like, I get it as like a birthday present. It's like one of those classic toys. Yeah. So yeah, that's how you can tell the difference between men and boys by the size of their toys. Right?
Size. Oh, I thought it was the
Yeah.
price, and now you're telling me I
That maybe it's the
the
price.
size.
Yeah, it's probably the price. Yeah, I think it's the price of their toys. Yeah.
About the size thing. All right.
Yeah.
So
Uh, and yeah, so I think we had a pretty good idea that it wasn't going to be February.
right.
And so mid-March has been, I guess, second week of March has
Yeah.
been the kind of the official target date, with maybe that meaning the 8th. I'm not sure officially if you go to the calendar what means the second week of March, whether it's the second full week of March or whatever. So somewhere around there,
Yeah.
expectation. We'll see.
Yeah,
So,
well, hopefully so. So, on the subject, so Optimus, of course, is what we talk about with Scott, and I've got three major categories. So again, I look at this from the standpoint of a factory owner, and this is very
mhm.
different than almost anybody else out. Certainly, anybody in our space in the community. You look at it from the standpoint as somebody who has helped people in factories put things together in those factories. But I'm looking at it as the owner. I'm looking as I want to reduce my costs. I want to reduce my overhead. I want to reduce my landed, what we used to call, my what it cost me landed on the factory floor. What's it going to cost me, and before I ship it out? And so the robots, of course, can impact that in so many different ways. And as I've been watching the whole situation over these last months, these three things came to me. First question was speed. My second question was maintenance. And my third question has to do with the hot topic of all last week, which is physics. So we'll talk about these three things.
Yeah, yeah.
All right.
Mhm.
Okay. So I'd like to
Sure.
start with speed. I think it's the most interesting. Everybody's going to be, well, maybe not, because the physics should really be interesting, but let's talk about speed. Right now, you've mentioned that the Optimus bot appears to be walking around the factory at about 1 mile an hour. And you're
Mhm.
saying humans, a nice pace is usually considered 3 miles an hour.
Yeah, that's a brisk pace, and I think maybe it's like 2.5 or something like that would be a reasonable pace within the factory. As going between these different conversions, I always mess them up, but the officially they usually use a pace of 1.2 meters per second.
Okay. All right.
And right now it seems to be walking the order of about half a meter a second, somewhere around that, or starting to get there. So still needs a little bit more, but the end of the day, it just comes down to, can it do the current task at the same rate? So even if it can't walk as fast, if you can find tasks that doesn't require walking at a great pace, that you can just execute the task on there, then that should be pretty good. So we're focusing on two parts. One is obviously the upper body, because a lot of times in most tasks, that's what's important. How quickly can you get the arm movement and everything else? And that seems to be progressing pretty well. In some cases, they're getting better and better. And part of it might be just the compute trying to decide what to do is just not there yet. And the other is also just the amount of energy or everything else that's sort of needed to consume it. They're very concerned about power consumption, because you want to get some real-time movement out of it, and
Oh,
also the walking speed. So I'd say from the waist up, they're doing pretty well. The waist down, not so much yet. And that might just be working on improving the gait. And I think someone kind of pointed out part of the reason is that these bots are expensive right now,
mhm.
and you don't want them to fall over too much. So you want to have them slowly learn to walk faster and faster. And yes, they're tethered and everything else, but in the end, you want to have them sort of untethered to make sure they're not falling over a lot. And that could be a little bit of what's holding back. It's just being concerned that they don't break the bots a lot. And we say bots dynamics show that when they get their bot going around, it fell a lot,
Yeah.
and it broke a lot trying to do it. And you can see all the scratch marks everywhere in their lab areas when they're going around testing stuff. So yeah, you
But
got to
by,
make sure you.
yeah.
Mhm.
But by the same token, the Boston Dynamics, certainly the dogs walk very fast, and
Yes,
the bots seem to be
yes.
closer to human speed. So you're thinking it's mostly about braking. I mean, are there any aspects of the mechanics that would keep it from going full speed?
I don't think so, because they did a pretty good analysis of the torque requirements of all the joints. So they simulate a lot of different walking gaits with the kind of payloads that they would have and the expectations of what they would need everywhere. And so I believe the actuators are there right now. It's probably just working on the control systems to make sure they have more confidence in just being able to be stable and not fall over. And they could probably go a lot faster right now, but it just might be consuming way more energy than they want. And so they have to make sure that they get a more efficient gate. And I think the other thing is just going to be come down to the feet, because there's a lot of mechanics in there that can make your gate a bit more efficient. So it's going to come in there. And remember, this seems to be almost across the board, is that, it's not just, Optimus isn't up at that speed yet, but you can also, look at Figure and some of the others that they can walk, and they cannot, they can get pushed and not fall over, but we have yet to see them going like full human speed, with the exception of Boston Dynamics. They list 5 miles per hour, and I believe it does 5 miles per hour because they've demonstrated that enough. Everyone else, they have aspirational speeds of 5 miles per hour, but I don't think they've demonstrated that yet.
So I think anybody, an outsider, a third, somebody who knows nothing about robots will be watching these robots, and they tend to, now, even as they're getting smoother and more capable, the upper body movement as well as the leg movement. So in both ends, it all seems to be kind of slow motion, like hesitant.
Seems to be that. And
trying, whatever it is, whatever the motion is, it's kind of slow. I would anticipate, I'm thinking, again, from a factory owner standpoint, I'm thinking I would like the bot not only to be as quick as my current employees are, I'd like it to be at least as quick, at least as fast as my best employee, but maybe I'd even like it to go a little faster than my best employee.
Yeah. Okay. You're getting ahead of your skis there, Randy. So let's at least, say it's able to do useful work, which means it's not slowing down the production line,
right,
and you're not losing money by using the bot.
Right.
And then eventually you can go faster. So I don't think you want to be that concerned with that it has superhuman capabilities right now. You just want to make sure it has near human capabilities. That's enough. Because in many cases, you will have a human worker who is very, very fast, but can that worker do it for 8 hours?
Right.
5 days a week? It's kind of tough because, sometimes that means that person is really expending an awful lot of effort, or, they figured out the trick sometimes that it's like they may actually have no effort just because they know they've mastered this particular thing. The other thing is you're right about hesitancy. And I think part of the hesitancy might actually be coming more from the neural nets trying to decide what to do, as opposed to mechanical limitations. And to use an analogy, FSD, there's so many times, I've gone out there and I know what my Tesla is capable of doing, and I have no idea. It's like, why is it hesitating in some of these turns? Sometimes like, just go. Okay. We know you can do it. So it's just, I'm not so sure. So it's more like the decision-making logic sometimes is what's holding it back, as opposed to the actual capability that's there. Because I know all I have to do is tap on the accelerator and it goes, and, it completes the turn. But for some reason, it's just deciding that it wants to be extra careful.
But we also know that FSD, if we want to use that example, we know that FSD will make as quick a movement as necessary with regard to steering, or as quick a movement as necessary with regard to braking.
When it gets the adrenaline rush like us, then suddenly it decides to perform. But a lot of times when I'm asking it to do a left turn, I was like, can you complete this thing? Are you going? And that's why sometimes I will intervene, is because I'm not convinced it's being aggressive enough. And it's like, okay, I'm going to go ahead and do that. And it might be that I could have completed it fine, but I just ran out of patience and like, I'm not sure. So again, that's kind of always the problem with doing the beta testing and the interventions that you do, is that if you don't know what it's really going to do, you're going to assume the worst case.
Right. Now,
you're the guy that's sitting in the car with this other car coming towards you, and you want to say, is this going to stop in the middle of the road? I'm just not sure. So I'm making sure I'm out of the way.
Yeah. And so in all automation, and it doesn't matter whether it's a robot or something else, we've been through it how many times with automobiles, and now with batteries, and with everything else with Tesla, as we've all been watching all this unfold. And so you start out with your line, if it's possible, you start out with it going at a certain rate, which you're not going to have a lot of fails, and then you speed it up, and hopefully you maintain your same level of efficiency. and then eventually you get it to its max capacity. So is that kind of the same thing that you would expect out of the bots, is that
Mhm.
maybe I do the job, I pick up something and move it over here, and now I'm gonna, if I do it right 100 times in a row, now I speed up that process and see if I can
Mhm.
get it right 100 times in a row going faster. Is that
Oh yeah,
the
yeah, yeah.
same?
It's just going to get better. It's going to be like any sort of ramp up, and that I'm not sure how easy it's going to be to dial up the bot. Usually they do that with industrial robots. Is that on your teach pendant, you literally slow it down to say run the thing at 10% speed until I'm confident that everything is going right, and then you just go ahead and say now run it at full speed. Um, I assume there may be something like that with these, to just to make sure they're doing a particular activity, um, or the bots will just kind of figure it out themselves as the training goes in there. And like you say, when the when their error rate just goes way, way, way down, when they get a really high OEE, then they might just say, oh, okay, we can let it rip. We can go a little bit faster. But yeah, it's like anything, is you're going to do it until you feel like you have confidence that everything is, that you can go a little bit faster, because there's just not something else in there that's going to be a limiting factor if you go too quick.
All right. So moving from that, I want to talk about this whole
Mhm.
big thing with AI and physics and all the things that have been coming up this
Mhm.
last week. And I, in my very untrained capability in the world of AI, and in science in general, my understanding would be that what we're seeing now with an end-to-end neural nets, what we're seeing with version 12, what we're seeing with the way that we're hoping the bots are going to work. What we're seeing with these videos that are coming out now, that are showing, crazy, crazy kinds of real world, but not really real world uh, things happening where the physics is correct. Uh,
Mhm.
this would seem to be really, really important for the robot. I mean, it's important for the car, but the
Right.
robot would need to know how to understand physics. And
Mhm.
you gave that analogy last Wednesday. You showed the video of the basketball player doing that turnaround jumper. And quite frankly, I'm a
Yeah.
horrible basketball player, but that was my
Steph
favorite
Curry. Right.
shot.
Yeah.
That was my
Yeah. Yeah.
favorite shot in basketball, was the turnaround jumper. And I was actually pretty good at it for some reason. And I always thought I was better at that turnaround jumper because you can't think about it. It's one of those ones
Yeah,
where,
yeah, yeah, exactly. And that was, I showed that one because there's like this example of proprioception, that
yes,
you, with your eyes closed, you know where all your body parts are. But also with your eyes closed, you can have an idea of an environment that you're very familiar with, where everything is. And so you can roughly know, because we navigate in the house all the time when the lights are out, when it's dark, right?
sure.
We have an idea, oh, if I met, this many steps to the door, I expect the door handle to be here. You grope around until you find it. It helps to have vision for that feedback, because we're not quite accurate on that, but some systems are going to be extremely accurate on that. But that was like before the Sora paper came out. And let's say that started an interesting chain of events that gets us an idea or an inkling of what's going on and where we might be in the development of the bots and their capability. So for those who don't know, is that, Sora showed the ability to, with a very simple text prompt, to create what are very realistic kind of video sequences, up to a minute long, that are very hard to tell they have some, obviously some examples, a lot of errors, and they may cherry pick what they released. But it's really impressive what they can do compared to before, where everything was more of a dream. All sorts of things would be wrong, and you're kind of wondering, it's like, okay, it's hallucinating, and we can't really trust the results. But now it seems to have a better idea of physics. To do some of these things, it has to understand how the world actually works correctly, to make sure that things are sort of physically correct. And I'm going to define that in a second. However, back in the summertime, Tesla referred to at a conference of some paper that was sort of indicating they're moving in that direction of being able to get a better idea of auto labeling and understanding the physics of the world of what was going on, and pre-generating scenes for FSD to get an idea of what to expect in the next 10 seconds of driving. So, and then to compare that with what you're seeing and use that as a way of like, oh, we need to deviate a little bit, or rethink about what's going on. And So John Gibbs had done a video about that back in the summertime, and he re-reviewed it and said, wow, this kind of confirms it. And he posted on X, and then he got a reply from Elon about it that gave us a lot of breadcrumbs. So it's kind of confirming that what FSD 12 is doing is something very similar to what Sora is, and taking like the current frames and using that as like a starting point and asking it to say, okay, what's it going to look like? Create the video sequence for the next 10 seconds out. And now, from that, use that as kind of training data, especially if things start to deviate a little bit. Elon also replied that they could have done the same thing by just giving it training data that was not related to driving. Mm-hmm. And he said that it is understanding physics. So physics in the sense that if persistence. So if an object becomes occluded, the expectation that it might show up. So if it's a pedestrian or a cyclist or something like that that's walking, goes behind a truck, the expectation is, oh yeah, they go behind trucks, and then they will show up after that. And you can try to do that heuristically, but it gets really, really hard after a while.
Yeah.
So the fact that they're able to do that, and what the thing is that you don't need to train FSD on anything other than scenes of driving. If you're going to start feeding it with all these other kinds of videos and ask it just like, what do you expect to happen next? It might start to hallucinate, and it might start imagining like, unicorns and UFOs and all these other things just to start appearing, because that's kind of what, it was like, no, we don't need that in there. So you want to make sure it's doing that. But that may be very different for the case like Optimus, where you need to train it on something other than looking at what's on the road, but what's in a factory environment, what's a home environment, and everything else. But still, you might limit it to like, let's not get the fantasy sequences in there. Let's really keep it to the real world. So what do we mean when we say physics? So it's going to mean different things to different people. We all have an innate understanding of physics and how things should work, and whether something is kind of real or not. And that's why, sometimes when a magician does something, we're like, well, wait a minute. It's like, that can't happen, even though it's an illusion that they've done, because they've been able to sort of trick us a little bit from our expectations of what's going on. But we have this, and it's very different than when most people say, oh, physics, you mean, Newton, F equals ma, right? And it's like, well, yes and no. So, Newton was the attempt to mathematically describe what's going on in the world, but we don't need mathematics to play catch. Right. We don't need that. And so we are not solving differential equations of motion every time we throw the ball. It's through experience that we have an idea of where the ball is going to go, because we kind of look at it and we are able to forecast the future position of that thing and know I got to run over there to catch that thing. Right. Okay. And then when you're a really good ball player, you go out in the field, something about the field conditions, the way the wind is, the kind of pitcher, the way the ball comes off the bat, the way it sounds. You kind of know it's like, oh, I got to run over here. So the guys, the experts, are a lot better than us. We're gonna solve that ballistic equation wrong every time. But with enough experience, you can go ahead and do that. So it's not solving those equations. It just has an idea.
Yeah, just to really bring it home. Yeah. Anybody that played any serious outfield knows that you know where the ball is going. You're watching the ball off the bat.
Yes.
That's when you make the decision where to start
right
running,
there,
right at the point where the ball hits the bat. No doubt about that. I was left fielder most of my baseball years, and that's when you make the decision. So it's pretty incredible.
And if you're getting a breeze one direction or another, you have to stand in a different place. The ball's going to carry further, or it's going to drop sooner. I mean, it's like, all those different things come in there, and but you're not solving the differential equations that come up with that. And when you want to throw something and hit a particular spot, exactly what you have to do that. So that's the difference between solving it. Now, obviously, if you're a gunner and you need to hit a certain spot on the horizon, you need these tables that are basically F equals ma. Yeah. And all those things to kind of figure out exactly where that's going to go to put it in. And that's very important for those applications. If you want to hit something a particular way, you need to solve that things, but you don't necessarily need that to be able to get really good estimates of how something is going to behave. And that's how we understand the world and the physics. So we know when we let something go, it's going to fall, how quickly it's going to fall. We know the idea that if two things hit, the expectations, how they're going to bounce off each other, all these things, but it does not mean you need it. Now, there's a lot of, it's pretty easy to solve simple sets of physical equations, when you start having a lot, it gets really hard and really messy quickly. So if you have a ball pit with lots of balls in there, in theory, you know how to calculate the movement of all those balls in the ball pit when you throw them on up there. But when you go to calculate, the reality of it is very difficult because of the interactions of all these different balls. So simple systems are very easy to solve. More complex ones become very chaotic right away, and you have no idea what the output's going to be. So if you go back to the example of Newtonian physics, the gravity is understood pretty well with just two bodies. So if you just have a very simple model of the solar system, sun and earth, you can predict where the earth is going to be billions of years in the future. But the reality is the solar system is an n-body problem. So just when you suddenly go to three bodies, it becomes really hard to calculate where those things are going to be over time. And depending upon your calculation method and everything else, they may all start out the same, but how they evolve over time can be very, very different. And you come up with different conclusions that oh yeah, the solar system is going to be very, very stable, or it's like, wow, suddenly it gets very chaotic, especially if you throw Jupiter in there. You can get these predictions that will say in a couple 100 million years, Earth will be ejected from the solar system, or maybe it'll be stably there. And a lot of that is because the systems become very chaotic and very hard to predict. And so that becomes a problem of, as you add complexity, you don't know. However, we usually have a pretty good idea of how things are going to evolve in the short term. It's like the long future is very, very hard to predict. And that also comes down to, what would be going on in a simple example. But when you start putting a lot of them in there, it's nice to have the neural nets. So a weather system is a classic example of something that's extremely chaotic, and all the heuristic compute they've done on that. Well, guess what? Some AI researchers started feeding like weather systems in and did a lot of machine learning on this stuff. And it turns out these machine learning algorithms are almost better at predicting the weather than these heuristically based ones. And that is like, wow, that's a really interesting discovery, that they're finding patterns in there that aren't showing up normally with heuristically, even though we think we're modeling it correctly, we're applying right kind of physics, because chaos is just weird. And and so what I'm starting to see is that what they're doing here, the fact they're doing end to end, is the way to solve these problems. Because otherwise it's way too chaotic and very difficult to understand. So that's kind of a long explanation, but
well, so I just thought of what might be a really good analogy would be billiards.
Yeah.
So you have in that situation, you might be doing a very simple shot, doing a corner shot. I mean, sorry, side pocket shot, where you only have a few inches between the cue ball and the ball you're hitting, and another few inches to the corner, and it's a small pocket. Or you might be looking at something where you're going to have to hit one ball, which is the second ball, and goes into the corner pocket, which is a wider pocket, but which is more, which is at a different angle. Anyway, all those things are happening. Or you might be shooting into a mass of 4 or 5 or 6 balls, or the entire set when you start out the game.
Yeah. And think about it, every time it's always different. Even though it seems like you're setting up everything exactly the same and hitting it, it seems the pattern you get at is always different.
Right. And you might be putting top spin or side spin.
You don't know. It can be the slightest thing. And of course, it depends on the pool table. Is the pool table level? What's the conditions of the cushions and everything else is a little bit different. And as we know, if it's a near shot, it's very easy to do. When it's very far away, it's very hard to do because the error accumulates over distance. It becomes a lot worse. So you really have to nail that. Combination shots are very difficult because it's like the slightest error right at the beginning, it just propagates through, which is why you get such radically different results. And this, again, is the nature of chaos, because you're looking at something that's basically a nonlinear system. Linear systems are very easy to predict. And the difference between a linear system and a nonlinear system is that when a system is linear, a small change to the input will result in a small change in the output. And they're also generally very easy to solve. We can come up with an analytical solution that we don't have to iterate to come up with these answers. So it's like always an exact answer every time. Small change in input, small change about it. Chaotic systems become very difficult because they're nonlinear, and just the slightest change in the input can result in a dramatic difference to the output. That's why it's extremely sensitive to the input state. So even though you think you're putting the exact same input state in there, it's almost impossible to have the identically same conditions every time you run that experiment or whatever else you do, which is why the results will be bad. Now, the systems may evolve kind of in a similar way in the early stages of it. But if you get down really, really closely, you'll see there is a slight deviation in there, and that deviation starts to magnify and accumulate and go out. So a classic example of a chaotic system is, like, we all know the pendulum. So you may have from physics remember the pendulum equation. That's very easy to solve. Everyone, high school physics, you learn how to do that. You learn it's not, you have to make this approximation between sine equal A, but for small motions and like that, it's fairly good and it's fairly understood how you can go ahead and do that. But now if you get a double pendulum, so a pendulum hanging off another pendulum, that is really hard to solve. There's no analytical solution. You can put together differential equations, but you have to solve it iteratively. So it's going to depend on time steps and everything else. But the most important thing is the initial conditions. So if you take it, and you can go out there and like look for YouTube videos on a double pendulums, and it's really interesting that you can put them up and hold it what you think is the same starting condition and let it go. And every time you do it, you get different results. So it'll go down and look all right and start swinging, and then we'll do something else, and then they'll do these traces of these patterns, and you can almost never get them to match. And the reason you can never get them to match is that you have to have identical input conditions.
Yeah.
Yes, if you put identical input conditions in, and if you solve it with like the same time steps, if you even change the way you try solving the equations, they'll come out very different. But when you look at the beginning, releasing that pendulum, it's all going to be doing exactly what you think right at the beginning. And at some point it goes crazy. So what's this got to do with like full self-driving and stuff like that? Well, the first 10 seconds of what you expect to happen as you're driving down the road, you can probably predict with a certain amount of certainty.
Yeah.
But if you ask me what it's going to be like 3 minutes from now, I mean, anything could happen. I have no idea what cars are certainly going to come on the highway and off. And I've got all these other autonomous agents that can do whatever they want. But the thing is, you've got a certain expectation of how the cars are going to drive, and you just keep on updating. So every 10 seconds, new set of initial conditions, reset everything, and let's look at the next, and let's look at the next. And then from that, decide if the system is evolving away from where I want it to be, then I have to take action. So I want to be in some narrow corridor that everything is okay here. But when things start to change, I want to reassess and what's going on to see what the expectation is. So it might be I'm driving down there and there's just myself and another car, and everything is safe. And if that car keeps doing what it's supposed to and what I'm supposed to, the next 10 seconds should be fine. But then I start to notice that car is moving, in a strange way that's a little bit out of what I'm thinking. Then I'll say, oh, stop. Now let's look at what that next 10 seconds is going to predict us. And the prediction is that car is drifting into her lane, is now going to be a hazard. So now you say, okay, I've got to start to do something a little bit different. So those are just examples of how it'll be good in the beginning and what you need to do to kind of keep it very stable. What Sora has done has made sure that the images are extremely stable and that it doesn't start to hallucinate and go off the rails right away. So you can get much higher confidence on what it's going to look like for that narrow period of time. And of course, if you keep on sort of resetting it and giving it new prompts, there's no reason why you couldn't make like a 3-hour movie out of Sora. You could probably do that. It's just compute limited. Yeah. And then speaking of compute limited, that's one of the things that Elon sort of referred to in John's post. And that was, they could have done it, but, obviously it doesn't make sense for that. And the other is they're just compute limited, but later this year, they won't be so much. So again, it's like, that might be some of the things that are slowing down some of the progress we're seeing in Optimus, because they may not have all the compute that they need right now to be able to solve some of these problems. And I'm pretty sure they're dedicating most of the compute to solving FSD and less so on the Optimus front.
Yeah. So I just want to drop back again to my pool theory. So if we can imagine, I'm sure almost
or billiards for those. We're not talking about the swimming pool.
Yes. Yes. So we have, you take the first shot, and after you've broken on the first shot, you now have a setup, and it's going to be pretty much the first time you've ever seen that setup, because it's never, the odds of it duplicating that setup is almost zero. And after you take the very next shot, you have now moved things around on the table to create a completely new setup again that maybe you've never seen, but you've seen analogous situations. So
Right.
having to build into
You
the
see that and you have to. Now,
yeah,
when you see a lot of these pool players making these trick shots, a lot of times they are setting it up in a particular
right,
way and getting the balls exactly where they need because they practice again and again with that same one. And someone who is really good is that it's like playing chess. You aren't thinking about what this move is going to be, but you're thinking many moves ahead. So a very good billiards player, they're scanning around there. They're trying to find the highest probability shot, but they're also trying to think, it's like, after I make this shot, what's the setup going to look like? What's it probably going to look like? Where's the cue ball going to be? Or where do I want the cue ball to
right.
be? And I want to make sure I don't disrupt the environment too much, so I can work off of that. And if they're really good, they can kind of get that in there. And again, it will kind of come down. It's like, oh, it would be ideal if the cue ball is over here. So how can I make the shot and get the cue ball over there? What kind of spin do I need to do?
Right.
That there is definitely the pool shark or the pool hustler going on over there, being able to manipulate the environment enough. Whereas you and I, we're just glad we can make that one shot. Okay. And then we're not sure what the scenario, the scene's going to look like afterwards.
So if we got the bot, if we've got, or we have a
Mhm.
neural net that is doing exactly the same thing, and
Yeah.
it's trying to learn to play pool,
Right.
which seems like a fairly simple game on the surface.
Yeah.
If it's learning how to play the game, it's watching game after game after game, and it's bringing all this content in, just watching it off the YouTube videos or whatever, or watching people play, or playing itself,
Mhm.
or simulations, all the kinds of things we've talked about. It would still take thousands of hours probably of content before the robot would be able to even do it in simulation, much less pick up a pool cue and go out and
There are
actually
some that are
start
going out there. So, I mean,
using it.
a lot of people work because in many ways, billiards is kind of your classic physics problems of figuring where everything is going. But I could see like optimizations that could be going on there. So again, you and I, we look at the setup, or you know, be playing 8-ball or something like that. The every shot we take, we are looking for the highest probability shot.
Right.
Whereas someone who's a really good pool player may not be taking the highest probability shot. He's putting together and saying, what is the highest probability of me? What's the best combination to make sure I can sink the next 3 balls?
Right. Right.
And that means that first shot you take may be a lower probability shot, but you're very confident that you can still make it, because you know after you make that, it's going to set up these other shots that are going to get easier and easier. So they're working all that stuff out. That's the idea of optimization. And you could imagine that the bots would be doing kind of a similar thing of figuring out what's the most likely or best order of operations to be able to accomplish something with a high probability.
Right, right. All right. So then this will be true in the workplace. This will be true for
Mhm.
the walking through the workplace.
Mhm.
So you have this idea then that you're trying to produce, which we've been talking about now for a few weeks, that instead of just trying to get a bot that can go in and drill a hole over and over and over again while standing in the same position, you're looking for a bot that can walk into that environment. Somebody can say, I need you to drill the hole over here. They can pick up the drill, go over and drill the hole. And then the person can say, okay, now I need you to drill the hole at this angle, but I need to on this other wall. And the bot is not going to become confused by its environment. It's going to have a general sense of its world and a general sense of how to use the tool, a general sense of what the application is, et cetera. And we think of it, and again, it becomes, we start to anthropomorphize, but it's not really thinking. It's really just creating this.
It's instinctual, yeah, in a way.
It becomes
It just
instinctual
yes,
in that
yes.
sense.
It's able to go ahead and do that because it's seen enough and it can infer. So one of the things that's been coming out with FSD 12, and this is one thing I forgot about. I just saw this morning and did want to bring up in this whole scenario, is that it looks like FSD 12 can do U-turns.
Right.
Whereas before there was like some sort of restrictions. And one of the members of the team, I think it was actually the Optimus team, someone's involved there, says like,
Right.
yeah, and that wasn't even trained for that. There was no coding for it. That was just like an emergent behavior that had seen enough examples of people doing U-turns that now it can do it.
Yeah.
So
Yeah.
that's like kind of exciting, because it means that the more training data you have, the more likely it's going to do it. And in many cases, it's going to figure out how to do things that you never trained it on at all, because it knows enough about the understanding of the world. It knows enough of the results that you want to get, that it's able to figure it out. And we do that all the time. You know, we learn a certain amount of skills, but at some point we figure out how to problem solve, even though we've never been shown that particular problem before, and figure it out from all the other experience of how to do it. And that's just a kind of a form of reasoning. And so now these are not playback units. These are now able to reason. That's the real kind of test when you start to get glimpse of AGI, is that it's really kind of reasoning on how to solve a problem, even though it's never exactly seen that one before.
Yeah.
And so that means, like, in a particular environment and everything else, it's able to abstract all these concepts to understand that a house has a bedroom. Okay. Every bedroom is going to a little bit different. Where it's in the house is going to be a little bit different. And it will sort of be able to figure out which room is the bedroom just by going around and exploring a little bit and say, oh, that must be what you mean by the bedroom. Now, occasionally there'll be a weird house where they set everything up in such a weird way that even the humans would be tricked into knowing that, no, that's actually the bedroom over there. You know, it's not the living room. Yeah. Because they got a Murphy bed or something weird like that in there. But for most cases, they will be able to go through, even though they've never seen it. And again, the kitchen will be the classic example. Sure. Everyone's kitchen is the same, but different.
Right.
Right.
Where are the spoons? Where are the knives?
But they're generally kind of in the same place. You kind of explore around there, and everyone else will, you know, some people will set up their kitchen like a really weird way. It's like, why is the silverware up in the cupboard over here? It should be in a drawer. I mean, if that's what someone wants to do, that's what someone wants to do. But, you know, we have a stove, we have a fridge. They're going to be in different locations, you know, left-hand door, right-hand door, French doors, you know, all the different kind of combinations to have it. But the fridge has generally, you know, a freezer area, a normal fridge area, you know, the crisper, you know, all those kind of things you're going to expect. Different kinds of stoves that you've seen enough of them, you can kind of figure them out. All in, it's like, okay, we got a 2-burner and we got a 4-burner and we got a 5-burner with like a warming plate or something. That's all going to be figured out once it's seen enough examples. So you bring it into a new house, it'll know how to make a meal, because just like you do, if I invite you over and say, Randy, whip me up an omelet, you can figure it out, right? You might say, Scott, you know, where's the whisker? You know, you look around like, Randy, we don't have a whisker in this house, you know. It's like,
yeah, somehow all of that seems easier than the pool game, quite frankly. The pool game seems more complex in terms of,
well, it is really challenging because you have to be so accurate on that. And I remember reading a book, Chaos, and it's just that, you know, they were claiming that, you know, to really understand what was going on there, you had to account for like so many effects, including like the gravitational effect of an electron on the other side of the galaxy. I'm like, what, really? It's like that's my excuse of why I couldn't make that shot, you know. I'll blame it on Beetlejuice, you know. It's like, I didn't quite you know, it was like expanding, you know, at that time. That's why. But no, so it just kind of shows that how chaos is just weird, and that's the slightest change in input can result in the thing evolving very differently than you expect.
All right, the third subject. So it's a machine. Optimus is a machine. It's not a human. It doesn't have flesh and bones. It uses mechanical parts, and mechanical parts wear out. You and I talked months ago on one of our shows. We talked about just the fact that it wears a little could impact its ability to do a certain task, and it would have to always be adjusting to the fact that maybe something has worn out a little. Now, that's very human too. I've got a little arthritis in my shoulder, and I definitely have to make some adjustments to how I do certain tasks so that it doesn't hurt my shoulder. So, so it's making adjustments based on wearing out. But what do you think? We're talking about these, certainly in the early days, the people that are going to be willing to spend the most money are going to be the people that have 4 shifts. So 4 shifts, 365 days. What do you think it's going to be like in terms of maintenance based on the equipment you're looking at, based on your years of experience with these kinds of pieces of equipment? Do you see this as being something that's going to be a maintenance nightmare, or is this something that it's going to be not too bad?
Oh, it should be fairly easy. So, I mean, the first they're doing, you know, design for manufacture to make sure they're easy to build. And I'm sure they're also doing like design for maintenance. And you can design for maintenance 2 ways. One, you can make it that you can only bring the car to the dealership. I always talk about the example of our Dodge Journeys, where what is normally a simple 20-minute procedure that you can teach your teenager for replacing a battery now requires almost 3 days. That's how long it took me to replace our battery because it's under the wheel well, you know, it's intentionally put in a place that you can't do it. So when you design a car properly, and the military is very good at not making those mistakes. Okay. because maintenance has to be done. And back when my first company started up, we were working with them quite a bit because they wanted to see the ergonomics, the accessibility, where they can get in, how hard it was, because they don't want to have that service nightmare. So things have to be designed to be easier and easier to operate and to maintain. So you have sort of the same problem on the factory floor, but you're kind of caught between two places sometimes, in that you need to do a lot of preventive maintenance to make sure the bots and your equipment, everything's going. And there's a normal service procedure, how often you're supposed to lubricate things and check things out, make sure they're going all right. And they also have a lot of algorithms on there to be able to tell when some piece of equipment is wearing out or is close to it, so that you replace it before it breaks, because you kind of can tell, oh, this thing's getting a little bit wobbly or it's making a high pitch noise. We know it will still be okay for a while, but let's swap it out the next opportunity so it doesn't take the line down. In many cases, it's difficult when a industrial bot breaks down on the line. There'll be normal maintenance items that you do in the off shifts. So you have end of arm tooling, which things are going to be wearing out. So if you're doing welding or grinding and stuff like that, there's always like these parts you just got to replace. You basically consider them to be consumables, and you design to make sure those are all right. But every now and then you could have some part of the mechanism fails. And that's like, well, we could, either see if we can fix it in place, or maybe take that end of arm tooling off and put another one on. And that's something that will just like slow the whole process down. Some cases, like if a bot really fails and has a problem, and it's not just like, oh, the wrist is acting up, we'll just swap out the wrist. It's just like, you got to pull the bot off the line. And that's not fun, because the bot is bolted down, it's behind safety fencing. It's like, deciding, oh, I want to move the piano from the downstairs to the upstairs. It's a procedure you've got to go through. So one of the things is these are designed to have, very, very high mean time between failures and a lot of critical components. So stuff like that doesn't happen. But still, it's going to happen, and you're going to be thinking about the nightmare scenario you have of being able to do it. And that's why there's always preventive maintenance. That's why you're always checking these things. With the humanoid bot, it's going to be a lot easier. So it's because they're already deployable. And if there's a problem with one of them, you just swab out the next one. The other is like the maintenance can be done in a couple of places. Doesn't necessarily have to be done right there. It's like we got two ways. We can take our car to the dealership, which is like, we just going to consider, oh man, what a pain, I have to drive there and stuff like that. Or someone can just come and fix it in their garage, right? And so that's sort of, what you could be doing with a bot is you can be deciding, do you have to fix it at the workstation, which you really don't have to, or the bot just goes over to some area, like going to the doctor. It's like there's a special area for being able to do it. And I think it looks like most of them are going to be very serviceable. So when they design it, first they're designing, the first principle in engineering is that you're looking at how many cycles you can get out of it. So you're going to design your wrist joint so it doesn't fail after 100 hours. Okay. You want to make sure you get 1,000,000 cycles or more out of something. And then if there is an item that is going to wear out because you got a joint that's just going to have a lot of movement in there, you make sure it's very easy to swap out and replace. And either it might be something you can actually do when the bot's right on up there, almost like, putting a Band-Aid on it.
Right.
It's simple as that, as opposed to, oh, we just can't do first aid here. You really have to go to the doctor's office. That's not a problem because it just goes there. So once you get an idea, if you're this big manufacturer, you just always assume, like what you do with your workforce. How many workers do I need? Plus 10%,
Right.
because the possibility that people are going to be sick and on vacation and all these other reasons. So you're already used to the fact that there's going to be something that happens that you have to account for. So you always make sure your workforce is a little bit bigger than you need. You just do the same thing with the bots. And then if a bot breaks down, you go over and do that. And then either you repair it where you are, or more than likely you won't have to, because you won't own the bots at first. It's going to be robots as a service, and it's going to be on the provider to say, hey, that bot's acting up. That's part of the services contract, right? You go take care of it.
Right.
Yeah.
And so, and you just mentioned that there's something I had been thinking a lot about over the last 24 hours, actually, and that is it's going to have a voice. And so currently our cars have voices. They don't normally speak to us. They have a text that comes up on our little screen, and it's maintenance required, or engine is boiling over, or whatever.
Oh, it's amazing.
It's
amazing. And a lot of it comes down with software. So, right now I'm getting an indicator that one of my tire treads might be a little bit low.
Right.
And, it's able to figure that out. It's like, you're getting extra revolutions on one side, you do the same thing. So there seems to be something wrong. You need to get it checked out. Of course, tire pressure indicators, low wiper fluid, stuff like that. But
Right.
there's other ways you can do it that people are doing in factories. And a lot of times is noticing sounds and acoustics. There's all sorts of information that can kind of come up from machines,
Yes.
power consumption, everything else. That's one of those things I think Palantir does with their foundry, is that they're able to look at a lot of things to tell when something is not acting right and could fail. And I know like the airlines have done a lot for preventive maintenance on a
Yeah.
lot of the stuff, is that they're able to tell that, yeah, this engine over here, it's like there's some indications in here that you might want to check something out way before the problem happens. And so a lot of the airlines have found that that has helped them a lot, because they've been able to diagnose these things way ahead of time and
Yeah.
make sure it gets fixed. And then they look in there and see it. So yeah, and a lot of that comes from machine learning data. The more data you get about the stuff, and then when failures happen, you can go through and start correlating some of the failures to some of the data sets that you're getting in there to be able to tell, that's an early indicator. And of course, like you get the guy who's been the machinist on the shop floor for about 40 years, and he's just got that ear
Yeah.
that
Yeah.
he could just
Absolutely.
hear something like,
Absolutely.
no, you might want to go over and check that piece of equipment out. And sure enough, you identify something.
Oh, absolutely. So actually the robot in this particular case could be very much like the fictional robots we've been watching in the movies for years, where it will go, oh, my wrist is not
It's going to know that it's because they do that a little bit. The way a cobot works, these are the robots that are working next to
right.
people, is they are doing an operation and they know how much torque all the joints are supposed to have. And if one of the force feedback sensors or torque sensors they have exceeds a certain amount, that's an indication that something's going wrong here. That means you may have bumped into something, and then it tells it to stop. Don't keep pressing ahead. It's like, that's out of norm. We got to look into it. So the bots are going to be the same thing. They're going to be doing the same task. And if they're starting to notice that, you know what, we're using a little bit more energy to do this, or we're just starting to get a little bit out of that spec, that's an indicator something might be going wrong, that there's a little bit more friction in the system, or that actuator is starting to fail or something like that. So they're just going to know that already. That data is there, and they will be able to correlate that very easily.
And maybe
Yeah.
self-diagnose it themselves, and then go
All the
over
time.
then go over to the repair station and repair themselves.
Yeah, yeah. The self-diagnosis, and then the data will probably get constantly uploaded, and then kind of review it again as they start to look at it. And then you could probably run some very simple tests even without going over there. It's like, oh, okay, like, let's just go through, lift the arm up. Let's test, which actuator is the one that we think is acting up and why it could be. So they'll know they're having a problem before they have a problem.
Absolutely, absolutely fascinating. What a world we live in. It's so incredible to think
Yeah.
about.
And then the last thing is like,
I almost feel like I
yeah,
should open a new
yeah,
factory so I get to play
yeah,
with it. Yeah.
yeah. If there's a problem with an actuator on the left arm, you're just going to swap it out with another left arm, and that's it. It's not like you have to go and fix that particular actuator. There will be these things that you just swap out really quickly. And then if the bot itself is just having a problem, just swap it out with another bot. I mean, it might be as easy as that. So the repairs will be pretty simple. And then at some point, someone can diagnose the whole thing down to levels like, oh yeah, it was just a particular actuator we can swap out. So there's going to be so many ways of being able to get them, let's say, back into service really quickly.
Very, very cool, Scott. Hey, as always, thank you so much for coming on and helping us to fully understand this, because again, this is the most important product maybe ever in history. And we are chronicling it. We're watching it. We're having fun diagnosing and guessing and making, having expectations about the future. We're invested in it. Most of us in this community are invested in it and could possibly even become quite well to do when the bot hits full application. And just the opportunity for the wealth that it's going to build worldwide. It's going to lift. Talk about Ronald Reagan's lifting all boats. This is going to be a case where the poorest people in the world they may not realize that the bot has made their life better, but because it will be making things that they need much less expensively than they did in the past. It gives them additional wealth.
What it's going to do is that, what would you do if you had such a huge source of labor? And one of them is that you could start using it to solve the problems that we can't afford to solve right now. Like, ocean cleanup of rivers and streams, making the environment better. I point you to the book Brighter by Adam Dorr, and some of the videos that he's done where he, explores that. you know, the fact that we'd be able to do rewilding of all these different areas, that the abundance of that will allow us to actually do these projects that we've always wanted to do. And again, that will be an example that it will benefit a lot of people.
Right.
And not to be too worried that all these jobs are going to be eliminated tomorrow. You know, it will be ramping up on this S curve, but it's not going to be displacing labor significantly for until probably mid of the next decade that you begin to see that. But by that point, the economy will probably have, let's say, rebalance itself, because everything always has to find an equilibrium. So if we had like 1 billion bots tomorrow, that will be a shock to the economy, and we still won't know what to do. We're not going to have 1 billion bots tomorrow. What we're going to have is we're going to have barely enough bots to replace the labor shortages we currently have. And as we start doing it, we'll be able to adjust what that is doing and begin to realize that, like, oh, hey, there are these projects over here we just cannot do because, you know, even at minimum wage, there's no budget for being able to do it.
Right.
And now suddenly you can start throwing them over there to take care of those problems, and everyone's standard of living improves. Quality of the environment improves, everything. Yeah.
People don't realize it. This will be much slower than what happened when email hit. When email hit, basically in about 5 years, you eliminated the category of secretary and stenographer, typist, those three together.
Right.
Those three categories combined were the #1 job in the world at the time that email hit. And within about 5 years, there was no such job category anymore.
Yeah. Once you started having word processors and everything else, you know, I definitely remember when I was a graduate student and working on, you know, having one of my first papers published, that there was a secretarial pool in the university for doing that. And then a few years later, you know, everyone starts having the laptops with Word on it, and then there was like no issue. You're able to go ahead.
Yep.
And take care of that. So yeah.
Great, Scott. Let's wrap it up.
Mm-hmm.
For those of you out there that are interested in this, you've obviously listened to this long. Go ahead and hit the comment button down there. Let us know what you'd like Scott to talk about next week. Give us some ideas of the things that are on your mind with regard to the robots, because it's a very new concept. It's a very new idea. The opportunities and the potential pitfalls are pretty significant too. Let us know in the comments below. And Scott, again, thank you so much for coming on.
Yeah, thank you, Randy.
Okay.
Yep.
All right. And to all of you out there, it's been great talking to you.